Fluid pressure. A force exerted on an object that is spread out over the surface area of the object is called pressure. Pressure equals force divided by area, or, rearranged, force equals pressure times area. For Pascal's first law, if any external pressure is exerted on a fluid, that pressure is distributed evenly throughout the fluid. Consider a container filled with an incompressible liquid. Pick a spot in the fluid at a particular depth h. All of the fluid in the container is at rest. Therefore, the fluid at depth h is in equilibrium. The sum of the forces exerted on the fluid at depth h must be 0. We see a force diagram here. The downward force on the fluid at depth h is from the fluid above depth h, and the fluid below the fluid at depth h exerts an upward force. The sum of the forces exerted on the fluid at depth h must be 0. It turns out that this downward force of the fluid above depth h, it's actually the weight of the fluid above depth h. So Earth exerts a force on the fluid downward, and therefore the fluid exerts a downward force on the fluid at depth h. So we can rewrite that as force that Earth exerts on the fluid above depth h. So we know that these have to be in equilibrium, so we can set them equal to 0. The upward force minus the downward force equals 0. And we can rearrange that, and therefore we know that those forces must be equal in magnitude. Okay, so the force that Earth exerts on the fluid above depth h, we said that's the weight of the fluid, which is mass times g. And the mass of the fluid above depth h is given by the density of the fluid times the volume of the fluid. So mass equals density times volume. So having that and putting that into our equation for mass, we get now that the density times the volume times g will give us that force. It turns out that the volume is actually the height h times the cross-sectional area of the fluid. So we can replace once again volume and get h times the cross-sectional area. So now we have the force that Earth exerts on the fluid above depth h to be the density of the fluid times g times h times this cross-sectional area of the fluid. If we divide both sides by the cross-sectional area, it turns out on the right-hand side of the equation that will cancel out. And so on the left-hand side, now we have a force divided by area, which we said is pressure. So we can replace that with pressure and get rho gh, density times g times the depth of the fluid, h. We did say that the fluid below depth h must exert an equal magnitude force on the fluid at depth h as the fluid above depth h to keep the fluid in equilibrium. So because those are equal in magnitude, we can just say that the pressure at depth h is given by rho gh, which is the density of the fluid times g times the depth, in this case h. Okay, for buoyant force. What is the buoyant force exerted on an object submerged in a fluid? Well, consider a cube with sides s fully submerged in a fluid. The fluid exerts pressure on all sides of the cube. The vertical sides of the cube are at equal depth and therefore have equal fluid pressure exerted on them. The vertical sides also have equal surface area. We know that force equals pressure times area, and so therefore the sum of the horizontal forces exerted on the cube is 0. So that leaves us with just the forces in the vertical direction. So in the vertical direction we have a downward pressure on the top surface of the cube and an upward pressure on the bottom surface of the cube. So we're going to call those PT and PB for pressure at the top and pressure at the bottom. We know that the surface area at the top and the surface area at the bottom of the cube is s squared. And we also remember that pressure equals force divided by area. So if we combine all those things together, we get that the force that the fluid exerts on the top surface is given by the pressure at the top times the area, which is S squared. And the equivalent for the force the fluid exerts on the bottom surface, which is the pressure at the bottom times the area. So, we know that the pressure at the bottom of the cube has to be greater than the pressure at the top of the cube because the depth is greater. So, when we go to make a sum of the forces equation, we say that the sum of the forces that the fluid exerts on the cube is equal to the pressure at the bottom times the surface area at the bottom minus the pressure at the top times the surface area at the top. So we remember that pressure is rho GH, so we can substitute that in, and we have to remember that the top surface is at depth h and the bottom surface is at depth h plus s. So that's where that comes from. So if we expand that out, we see that we actually have two terms that are going to cancel, the first term and the last term. And we just end up with the sum of the forces that the fluid exerts on the cube is given by rho g s cubed. But remember, s cubed is actually the volume of the cube, so let's replace that. And then we know that volume is mass divided by density. So if we substitute that in for v, the density actually cancels out, and we end up with the force that the fluid exerts on the cube is given by mg, which is in fact the weight of the fluid that's displaced by the cube. And so that is where our buoyant force comes from this pressure differential between the bottom surface and the top surface, and we know that it's equal to the weight of the fluid that has been displaced. Thank you very much.